Buffer.
And technically it is a buffer, yeah. An amphoteric compound. An amphoteric compound acts as both an acid and as a base. So in that top case, if it's acting as an acid, what do we get? End up with the sulfite ion. Because it acted as an acid, it donates the hydrogen. Okay, we would know that because that is the definition of a Bronsted-Lowry, or officially even an acid in general, that you should remember from 152. Plus, what's the other species or the other product? NH4 plus. In this case. Okay. Being able to look at your reactions and predict your products. This is something you were responsible for in Gen Chem. At least you should have been. I don't know if you actually were or not. Okay. In organic, we take it to the next level. Okay. So you will be expected to be able to predict these, but you will also be given a situation like we have with HSO3-. That compound can act as an acid or a base. How do I know which it should be acting as? Okay. What we're putting it next to. Okay. That can be a useful hint. Okay. Other things that we'll look at will be evaluating the acidity constant, or our Kas. Okay. Remember solving for Kas, right? Predicting those. And we could use Kas to predict which way a reaction went. Yeah, doing all those fun calculations. Okay. You don't have to do any calculations. You just have to be able to look at the number and decide its relative position to a point of reference. What might be a good point of reference? Water. So if you know the pKa's of a lot of different functional groups, you can compare them back to, say, the pKa of water and decide, is it more acidic or less acidic than water? And that can help you predict something about our acid-base reactions. In the bottom case, what do we end up with? OH minus and H2SO3. So we've got our two products in the bottom case. I also asked you to go through and label. Provided two labels for you already. How many more labels are necessary? 6 of them are necessary. We've got our base here. We have our base here. How do I know it's a different base? I can call it the conjugate. This is something that I don't understand comes through in Gen Chem. They reference conjugate partners as both reactant and a product. When we look at conjugate partners, our conjugate partners will always be located on the product side of our equation, the right-hand side. Okay. Simplify. Our ammonium will be our conjugate acid. How do we know that? It's a proton donor. So what we can do is look at the reverse reaction. Okay, to go from NH4 to its conjugate partner, the NH3, what has to happen? It has to lose H+. Okay. If it loses H+, it is an acid. Okay. So by applying the definitions of what our acids and bases are, we can start to come up with better predictions about what's happening in our equations. And we would also have our conjugate base and our conjugate acid. All solid review, right? Easy? You're like, yeah, that was too easy. Sure. Okay. Should we step it up? Okay. So let's look at some definitions. Okay. Arrhenius was our first definition, which is the one that you typically use in 152, albeit it's kind of an obnoxious definition. What is the Arrhenius definition? Our acids generate H+, and our bases generate OH-. This is great when we're looking at solutions in water, okay, in an aqueous environment, which 152, everything's in an aqueous environment, so that definition is great. Okay. However, it is very, very narrow. Okay. What we want to do is expand our definition to apply to things more than just H+ and OH-, just than water. So we can move out to our Bronsted-Lowry definition. They expanded it just a step further and said, okay, let's not look at it just as OH minus. I want to look at it as a species that accepts H+. Well, does that actually change the definition? What would OH minus do as a base when it reacted with an acid? It accepts H+. Why would they react with each other? Negative and positive. The opposite charges cancel. Okay? The conditions that we see within acid-base chemistry of a positive and a negative reacting, guess what we see in organic chemistry? The exact same thing. Nothing changes. It is still finding a negative and finding a positive and putting them together. How do we put them together? Well, that's chapter 7, looking at each of the mechanistic steps. What are the possible ways that we can put a very positive and a very negative next to each other? Okay. H+, you'll typically hear referred to as a proton. Okay? This is not a proton reacting with a nucleus. This is a proton that's acting as a bond. Okay? So it's not going into a nucleus. It is occupying space. So some other quick practice. We now have some definitions. H+ donors are acid, OH- donors, and H+ acceptors are bases. So label those, and let's see what you guys come up with. Acids, bases, or neither. Next one. Next one. Okay, how would it act as an acid since you're saying both technically? What's our definition of an acid?
It gives a hydrogen, but technically it can cancel out the negative charge.
So sodium chloride has no hydrogen to donate, so it doesn't fit our acid-base definition. Okay. And I heard most people say, what did you guys say actually? Neither. Okay, really? What do I get? Sodium sulfate and? What did sodium chloride act as? It acted as a base. Why did you guys say neither? Or neither?
Because as it is sitting by itself, it doesn't have the ability to accept or donate any hydrogen.
I will agree with the donate, okay, but up in the base condition, okay, you said it could accept hydrogens. Why can you not accept here?
In the state as it is, it doesn't.
In question 4, in the state it is, it's not accepting hydrogen. Why'd you call that one a base and not 5? And let's put it this way, no. 4 does not have an OH. That is an extremely dangerous mistake that is very common. There is no OH in either 3 or 4. Okay. And for those of you that don't see that, let's draw that out real quickly. That's what we've got for that structure. This is not OH. Okay. It is a carboxylic acid. Okay. Which means that hydrogen is acidic. Okay. It is not an OH group. How do you know you have OH? For it to be a base, it must be OH minus. How does it get to be negative? What do we have to attach that OH to? A positively charged atom. Is carbon positively charged? Is any nonmetal going to be positively charged? No. How do I get that to be OH as our base? I said nonmetal. Attach it to a metal. That is the only time it becomes OH. Okay. So if we drew out another structure. Oh, that was the wrong button. Does this generate OH minus? No. Even though there's an OH atom there, or OH group, that oxygen is connected to the carbon, okay, which means we don't have hydroxide. Okay, whether it's an acid or a base is a separate question. Okay, so let's go back to our original question, our original issue. You guys labeled 4 as a base, but then you said 5 was neither an acid or a base, and I quickly drew up, relatively quickly, this result, in which case sodium chloride acted as a base, accepted hydrogen, right? Okay. Why, again, did you say 4 was a base and sodium chloride was not? And again, you did it correctly. No?
Have experience with this pH.
There's an actual interesting point. You have experience, and I'm going to ignore balancing this, so please don't call me out on that. I'm aware it's not balanced. What's your experience telling you?
When you have salt water, pH is different.
Okay, but why? Why does it not change? HC2H3O2, what can you tell me about it? That might be kind of a hard question, so let's make it easier. What can you tell me about HCl? What do strong acids do? Completely dissociate into their ions. Meaning, as soon as I make HCl, what happens to it? It breaks apart. Meaning, it never accepts hydrogen. How did I get it to accept hydrogen in this case? What can you tell me about H2SO4? Not only is it another strong acid, it is a stronger acid than HCl. Meaning I can force that reaction to occur. When you look at 152, we kind of simplified things. You said, here's strong acids, memorize them as strong acids. Do not ever make them in a reaction, because by definition they're strong, and we shouldn't make them. They immediately need to break apart. Right? So you are correct in looking at number 4 and saying that that one's a base, and you are correct at looking at 5 and saying that's neither. Okay? And it comes from having memorized those strong acids. You knew this. You did good. 6. What's the deal with 6? What'd you pick? Now you're all like, oh, he's going to tell me I'm wrong again. We heard neither again. Yeah, sorry. And yet, what happened? It donated a proton, which means it acted as an acid. Why did you guys say neither? Okay, it's organic. That's one possible option. But number 3 is also organic, so I don't quite accept that. Why, when we looked at number 3, you could label that as an acid, but in this next one, or number whatever that one was, you said no, it can't act as an acid. Not polar, what do you mean? Take that further.
It wouldn't easily donate that in a normal state.
Why does it not easily donate that hydrogen?
You don't have an electronegative atom that is pulling electrons away.
What is the hydrogen connected to in number 3? Oxygen. What is the relationship between oxygen and hydrogen? Massive difference in electronegativity. Oxygen is the second most electronegative element. Meaning, what is it doing to the electrons in that bond? It's taking them. Push it to the extreme. It takes them all the way. What do we have left? What happens in the case of methane? We'd have to do the exact same situation. Where would we put that negative charge? On carbon. Why are we saying that's a bad thing to do? Why is it not stable? Why was it all of a sudden stable up here in 3, but now not stable in 6? Carbon doesn't want to hold on to the electrons. I agree. Why? Give me science. Electronegativity. The electronegativity of carbon is lower than the electronegativity of oxygen. Okay? Meaning that carbon does not pull the electrons away from the hydrogen. If it can't pull the electrons away from the hydrogen, can the hydrogen float off on its own to react with the ammonium? No. Okay. So we have to now start to look at our structures and evaluate how can these things possibly react, coming up with rules to predict acid and base characteristics. Okay. We could go through with that last one, same deal. NH3 acts as a base, exclusively as a base. Okay. Horrible as an acid. The reason we are able to predict a lot of these is because of your experience. You, based on your experience, told me 5 should have been neither. Based on your experience, 6 was neither. But you didn't have a way to quantify it. You just said, it just doesn't. It doesn't do it. Okay? We need something more than that. That quantification is ultimately going to come from understanding some rules about predicting acid and base characteristics. And when we look at just a straight structure, it is going to be very difficult to decide, is it an acid or is it a base? Because in both those cases, our acid-base nomenclature comes down to what is it reacting with. Okay? So when we look at an individual species, we need to come up with a guess. I don't think that should act as an acid. I don't think that should act as a base. Then I can throw in another species and be like, whoops, okay, I need to refine my choice because I'm now put under a situation that's going to force it to act like one of those. Okay? But you need to have that gut instinct coming out of it first. Okay? So, back to our acids and bases, looking at our definitions. Okay? When I refer to acids and bases, I'm referring exclusively to one of the 3 definitions up here. That definition is Bronsted-Lowry. Okay? Yeah, it was a 1 out of 3 shot, not a bad try. Okay? Acids and bases, in my terminology, refers exclusively to our Bronsted-Lowry acids and bases. I am only looking at the exchange of protons. The Arrhenius definition, you'll notice, is not listed up here. Why? Because it sucks. Okay? It is way too limited in its scope to do any use for anything in the real world. Okay? So we need to expand that definition outwards. That first expansion came down to Lewis, and instead of looking at the locations of where atoms moved, he looked at the location of electrons. Atoms don't technically move when we're looking at our Lewis theory. Okay? What moves are the electrons around those atoms. That's what's causing the different bonds to form. Okay? Have we already been using Lewis theory? How do we do resonance? We moved electrons. Why? Well, resonance ultimately came from what kind of structures? Lewis structures. I wonder, is it the same guy? Yes. Yes, it is. Okay. Massively important. So broad in terminology that it applies to every single reaction that we can do. Almost. 99% of them. Okay. So the definition of our Lewis acids and our Lewis bases, we'll look at how the electrons move. An electron acceptor is a Lewis acid. An electron donor is a Lewis base. Okay. In and of themselves, that's fine as a definition, but that applies to every single reaction. Are all reactions the same? What happened in this first reaction? What changed? Just tell me what changed.
You gained a hydrogen bond with the oxygen.
So that hydrogen appeared. Okay. Two things happened. I lost an H from one atom and I gained an H, that same H, to the other atom. So what happened in the course of this reaction? Okay, moved from one location to another. That is all that happened in that equation, right? Nothing else. What happened in the one below? I broke a bond. for that bromine and ultimately made a bond. What did I do in the first reaction? I broke a bond and I made a bond. Isn't it the same thing? Why is it different? One's hydrogen and the other one is not hydrogen. There's our delineation between these two types of acid-base definitions. Our Lewis definition is acids and bases, but it applies to every type of reaction. We have two major subcategories we can run. We've got our transfer of hydrogen, Gen Chem stuff, okay, which we don't spend a lot of time on because we expect you to know it. Okay? We'll keep doubling back to it to keep reviewing on it because there are some important rules that you probably missed. Okay? The other case, transfer of So what we're going to do is divide out these two types of reactions. In one case, we'll refer to this top one as acids and bases. It is a strict acid-base reaction because it is only transferring a hydrogen. This fits our Bronsted-Lowry definition perfectly. Okay. In this bottom situation, there is no hydrogen ion being transferred. So we don't want to use an acid-base definition because that's now going to get confused. We want to invent a new term that still applies those same rules. That new term, nucleophile and electrophile. Describe a proton donor for me. What would you find within a proton donor for an acid? HCl, right? Our classic acid. What do we have? H plus and Cl minus. If we shift our focus from it being the transfer of a hydrogen ion and instead look at the electrons, what does this species need to do to react with a base? It needs to accept electrons. So our Lewis acid is an electron acceptor. I now want to come up with a new term to describe that. Okay? That does not get confused with its acid-base definition. Okay? It is something that is positively charged. Okay? It accepted electrons. Okay? It wants more electrons. We might go as far to say as it loves electrons. And something that might love electrons could be called an electrophile. All by looking at just your standard definition of an acid or a base. We're looking at something that is typically positively charged. If we look at our bottom reaction, where's our good example of our electrophile? Which species accepted electrons? Okay, I heard the ring. Okay, you're probably zooming in on that one. Why'd you zoom in on that structure? It's positively charged. Cool. Is it just the ring? Can you get more narrow in that definition? Of which one's the electrophile? The carbon holding the positive charge. Did we start with this structure? No. So labeling this as an electrophile once we've drawn out the reaction kind of works. But I didn't start with it. Where's the electrophile in the starting point? That is still the electrophile. Why is that still the electrophile? We have a polar covalent bond. The chlorine is pulling electrons away from our hydrogen, making our acid. What does the bromine do? Pulling electrons away, making the carbon partially positive. There's our electrophile. How do we predict all that? Electronegativity. Okay. We've now defined our electrophile. Well, what's happening for our nucleophile? So our nucleophile, nicely color-coded if we notice that. Let's go back to our standard definition, which you already know. Our bases are proton acceptor. Give me an example of a proton acceptor. Hydroxide. What does hydroxide do when it reacts with an acid?
Electrons on oxygen.
the electrons on our oxygen share with that positively charged hydrogen. Our base is an electron donor. It is shared electrons with some other atom. That's our definition of a Lewis base. Still applies to our Bronsted-Lowry definitions. Okay, Lewis acids and bases will apply to Bronsted-Lowry every single time. The nucleophile electrophile cannot be referred to as Bronsted-Lowry. Why not? Our definition of our electrophile and nucleophile was other stuff, not hydrogen. By definition, they can't apply to each other. Lewis overarches everything. So we now have an electron donor. How can I come up with a name for the electron donor? This one's a little bit less intuitive because in an electron acceptor, we can at least say says it loves electrons. Okay? So let's try and maintain that same nomenclature or idea behind it. We need a file. It says loving. Okay? We could try hates electrons. I have no idea what the Greek is for hate, so that doesn't work. Okay? What is that nucleophile reacting with? Okay? If we just say proton, that's Bronsted-Lowry. We can't say proton.
But it's the nucleus.
It's something that is positively charged. Right? You can't say it's hydrogen. It's something else that's positively charged. Okay? Well, if I think back to atomic structure, where is the positive charge located? In the nucleus. So what I'm looking at for an electron donor is I'm looking for a nucleophile, nucleus loving. Does that breakdown work every single time? Yeah, you get lots of back and forth within it. This is why it's important to know those definitions. I can almost guarantee it on your next test you will have a strict what is the definition of a nucleophile. Okay? Because understanding those definitions is critical to being able to evaluate your mechanisms. Okay? Questions?
I have a comment on the
Yeah.
opposite of file. According to the thing I just kind of skimmed, phobia would have been the opposite because
Phobia,
fear is the opposite of love.
That's true. We could have done electrophobic. We do hydrophobic and hydrophilic. Too bad. We didn't do it. Okay. Next fun part. This is really just a factual thing. Realizing what your arrows mean. Okay. Not all arrows are created equal. We've seen reaction arrows. We've seen equilibrium arrows. Okay. We've even seen double-headed arrows. When did we see double-headed arrows? In drawing all of our fun resonance structures, we would need to show a double-headed arrow because it's not a reaction. It's not an equilibrium. They are identical. Okay? That's why we needed a different arrow. Okay? We've also seen these full-headed curved arrows. What do the full-headed curved arrows show? The movement of our electrons, because it goes back to Lewis theory and the motion of how our electrons shift. Okay? When we've moved our arrows or used our curved arrows, you'll notice that how many electrons do we move at a single time with that arrow? 2. It's always been 2. Why? Okay. We like forming pairs. Okay. Within a bond is a pair of electrons. So if we're going to break a bond, it makes sense to move a pair of electrons. When we look at our curved arrow, how does that represent that we've moved 2 electrons? There are 2 sides of our arrow. Okay. Do we have to move 2 electrons? No, I could just move 1 if I felt like it. Okay. I need special conditions to do that. I would have to change my arrow, though, because the arrow on its own shows 2 electrons. So what I'll do is shift it to a half arrow, okay, or a fishhook. These are going to be used throughout this semester, throughout the rest of this semester and next semester. You need to know what they mean. You need to be able to use them. Okay? This summarizes their uses and gives you common times when they show up. Okay? So make sure you know those. Yes?
We won't have to worry about moving more than 2 at a time.
You will never move more than 2 electrons at a time with a single arrow. If you need to move more than 2 electrons, what do you need? You need more arrows. No, that's a good question. So, bond breaking and formation. Okay, these are only going to involve our outermost electrons. Okay. What we're trying to do is, again, show the motion of the electrons. This is something that's kind of annoying. Organic chemistry very seldom balances reactions. Okay. I've heard students complain about it before. I am trying my best to balance reactions, at least initially, to help you be able to identify and see those arrows. Okay. It is very difficult to balance reactions. Okay. I will try. If you don't see something balanced, let me know and I'll try and adjust it on the fly. So let's take a look at that first reaction. Number one, is it balanced? Okay, good. At least did one step right. All right. We want to now add curved arrows to this to explain what happened. When we used curved arrows before, we used them with resonance. And in resonance, what electrons can you move? Lone pairs or pi bonds. That's it. Okay, because we cannot make or break sigma bonds because then it's not a resonance structure. It's a different compound. But what are we doing now? We're making new compounds. We're destroying old compounds. By definition, we can now move sigma electrons. Which sigma electrons should we move first? Lots of different answers floating out there. The simplest answer, the most reactive electrons. You should move those. How do you know they're more reactive? How do you know they're higher energy? Yes. We could look for charges. Wherever there's a charge, what's our molecule going to try to do? Neutralize that charge in whatever fashion it can. So if we take a look at that first example, where is the reactive atom? Whoops. Where is the reactive atom? Which oxygen? The one with the positive charge. Okay. How can that oxygen react to become less positive? Okay. We heard lots of interesting answers here, none of which referred to the electrons. The electrons are the only thing we can touch or move. So you cannot do anything other than focus on the electrons. What can I do to stabilize that positive charge? Give it electrons. Okay, and give what electrons? The oxygen. Why? I'm trying to neutralize the positive charge. To make something less positive, what does it need? Sorry, that was weird. No, I was not trying to wink at you. Oh, I don't know what's going on. I'm just going to close it. Not really. Let's say a positive charge. Okay. So there's electrons over here, right? And lone pairs tend to be higher in energy. So let's take those lone pairs and let's share those with the oxygen. Okay. So you might already guess that's not going to happen because you saw the answer that was up there already. But what else is wrong with that? How many electrons are around the oxygen right now? 8. If we give it more electrons, what happened? It exceeds the octet. Can we do that? No. So if we exceed the octet, we'd have to break a bond. So let's say, sure, fair, let's do it. Let's give it those electrons. We need to break a bond. What bond do we break? We're going to have to keep our focus where? On that same oxygen. Why on that same oxygen? It's the one that's exceeded its octet. So I now need to ditch electrons. What electrons do I have as an option to ditch? To the hydrogens. Okay, would I have stabilized my octet? Yes. Yeah, okay, so let's do it. What do you get as a product? I'm not drawing stereochemistry, just so you know. I don't want to deal with it. What is that oxygen attached to? The other oxygen. What is that oxygen connected to? 2 hydrogens. What happened to its lone pair? Still there. What happened to that last hydrogen? Ah, 2 good answers floated out of there, an H plus and an H minus. Okay. What happened to the hydrogen? It took the electrons, which means it's H minus, not H plus. So good, you addressed formal charge on the hydrogen. How about the formal charge on our oxygens? Remember when I said you need to be able to look at a structure and decide formal charges quickly? Okay? And I said you need to be practicing this to make sure you can get it down so that when you look at a structure you can say that's the charge on that atom, this is why. Okay? We're going back all the way to chapter 1. You need to be able to identify those formal charges quickly. And as soon as you've done that, you should now be screaming, that was really dumb. Why'd you draw that out, Mike? Because you need to see how to do it wrong. Okay? Why is this a really bad idea? Two positives right next to each other. Okay? Like charges repel. This molecule's freaking out right now. Okay? Another reason why it's bad. Oxygen is very electronegative. I'm not sure I understand though. It was positively charged to begin with though.
The second structure is even less stable than the first structure.
Okay, why?
Because the positive charges on the oxygen, negative on the
We have
hydrogen.
two positive charges next to each other. That's bad. Why did we do all our initial arrow pushing? To neutralize the charge on that oxygen. What happened to its charge? Nothing. Did we do anything to help it? No. What does that mean? Bad drawings. Okay. Another thing that came out, we have this H minus. How stable is H minus? Not stable. Why is H minus not stable? It's got 2 electrons. H minus by definition has 2 electrons. Yes, it'll bond to whatever it's nearby, but that's going back to the same statement saying that it's not stable. Why is H minus not stable? It doesn't like the electrons. Elaborate. Oh, interesting. Right back to our initial definitions that we've been using. Hydrogen is not electronegative, meaning it cannot hold the negative charge. Electronegativity might be an important thing to evaluate when looking at how our reactions are going to occur. Okay? And evaluating if it should work. There's another reason why hydrogen's horrible at holding a negative charge. Give me an example of an atom that holds a negative charge well. Chlorine. Fluorine does it, but chlorine does it better. And I'm just going to pretend you said chlorine, even though I've recorded that statement. Why does chlorine hold its charge, that negative charge, better than hydrogen? And don't tell me electronegativity. You already said that. I think you said it.
It's a bigger atom.
It's a bigger atom. What does that mean? What makes that structure reactive? Both of them are reactive for one reason and one reason alone. The negative charge. Charge is bad. You touch a negative charge, you get zapped. Okay? Horrible, miserable pain. Here's a hydrogen. There's the electron. Here's chlorine. Here's the electron. Electron doesn't change its size. Still an electron, right? You are now forced to stick your hand into one of those two circles. Which one do you prefer to stick your hand in? Okay. Why would you stick your hand in the bigger one? There's less chance of encountering the negative electron. What we've done is taken this electron and we've spread it over a much larger area, like we do when we do resonance. Okay. Size is resonance. They're the same concept. Okay. Hydrogen, what can you tell me about its size? The tiniest atom that we know. Okay. Cannot hold a negative charge very well. Okay. So all of that taken into consideration, we can erase everything, go back and say, okay, I need another way to stabilize that oxygen. How do we stabilize that positively charged oxygen? I cannot give it electrons from another source because that went south real fast. Where else are there electrons? In the bonds right next to the oxygen. Like right next to it. like really, really close. Let's look at those electrons before we start looking outside the structure. So let's take the electrons and say that bond, and let's put them on the oxygen. Does it matter which bond I use? No. Why? All the same. Okay. Now what happens? The charge is neutralized on the oxygen, but what happened to the hydrogen? It becomes positively charged. Okay? Hydrogen would actually be missing its octet. And as we learned, albeit not very happily, when dealing with resonance structures, when we're missing our octet, we have a bad Lewis structure. So we need to somehow stabilize that positive hydrogen by making sure it gets its octet. How can we ensure that it gets its octet? What does it need? It needs electrons from another source. We can't use the oxygen that just took the electrons away, so we need to find a different source. Where's our different source? The other oxygen. And what we've now done is shown how we make those products. Everybody understand that? Okay. I tried to go really slow through that. I don't know if that showed. Did that show? A little bit? Okay, how about the next one? We had curved arrows to the next one then. What changed in that very first step? The bond between the carbon and the bromine broke. So I found my source of electrons. Interestingly enough, that's my reactive source of electrons. Why would I pick that as my reactive source? It's a polar bond. Bromine is very electronegative, causing that bond to polarize, making those electrons the highest energy and most reactive. How else do we know that those electrons are the ones that are going to react? Look at the product. What does the product show? It shows there's no bond. Okay? Where should the electrons in that bond go? Okay, why to the bromine? Ah, good answer. You actually gave the full answer. The electrons should go to the bromine, not to the carbon, because bromine is more electronegative than carbon. The electron should shift towards the more electronegative element. What's the other answer? Look at the product. The bromine gained a pair of electrons. The electrons had better have gone from the bond to the bromine, otherwise we created stuff. Okay. By breaking that bond, we generate two new charges. We have a positively charged carbon and a negatively charged carbon in our, bromine. Okay, now what's our most reactive thing? Okay, focused on the positively charged carbon. Why is that reactive? It is charged. Why else is it reactive? It wants electrons because it's missing its octet. Why are we not looking at the bromine? It has its octet. Why else are we not looking at the bromine? It's still floating around in solution, but why'd you not look at the bromine? So you've evaluated and said, well, that's not the product. Okay. More reasons. What'd you say? Stable. There's a good answer to be asking why. It's stable. Of course, now the next question will be, why is it stable? It is larger. Bromine is a very large atom, meaning what can it do with the electrons? Disperse them over a large area, making it more stable.
So it's okay with the negative charge?
It is okay holding that negative charge. It can hold that negative charge relatively well. Why else would that negative charge be okay on the bromine? It's electronegative. That's why the bromine is more stable. Okay? We can now look at our solution and say we've got this positive charge. We said the bromine can hold that negative charge fairly well. I've got a positive charge. I need to kill that positive charge. How do I kill the positive charge? I need another negative. Where do I get more electrons? Okay. Which lone pair should I use? The carbon or the nitrogen? Carbon. Why? Give me the easy answer. Look at the answer in your product. There's easy answer number one. Easy answer number two, look at the charge. Carbon was negatively charged, not the nitrogen. How do you know that? I've got the negative kind of floating closer to the negative or to the carbon side, but when we draw out hydroxide, right, where do we put the negative? When we look at hydroxide, where's the negative? It's on the oxygen, not on the hydrogen. So I don't quite accept that.
You know, there's only 3 bonds on the C, on the carbon.
Well, there's 3 bonds on the nitrogen.
But that's that, it likes that.
If we remember something about our bonding characteristics between carbon and nitrogen, carbon wants 4 bonds, nitrogen wants 3 bonds. There's already 3 bonds between the carbon and the nitrogen because I recognize my Lewis structures. I don't want to put another bond to the nitrogen. Okay? Another reason. What is the difference between carbon and nitrogen? Nitrogen is more electronegative. Why is that helpful for us?
Because then it would just have another charge on it and would cancel out the...
Not quite.
The nitrogen's going to want to hang on to electrons, and carbon's going to want to get rid of it.
The definition of electronegativity is holding bonding electrons. Given the choice, which atom would share bonding electrons? The carbon, because it's less electronegative than the nitrogen. We process like 60 billion reasons for why the reaction should work. You need to be doing this exact same thing all the way through. Okay? This is one of the reasons why I think students tend to be like, well, I don't know how to start this next question. To answer these 2 questions that we just went through and did, we spent probably 20 minutes doing each one. 10 minutes each one. Okay? In those 10 minutes, what happened? Was it just, oh, we need to do this? No, it was, what do I do now? Why did I do that? Why did I do that? Why did I do that? How many of you wrote down the questions that I asked? Okay. You will have a very hard time starting any question or any problem because you're looking at the big picture and not saying, well, what do I do now? What do I do now? Why did I do what I just did? You need to be asking those questions. Okay. Resonance and mechanisms. Same rules pretty much in both sides. You're finding a negative charge and you're attacking a positive. Okay? We're shifting electrons around in a structure. When we deal with resonance, we're only looking at lone pairs and pi bonds. We cannot touch sigma bonds because we can't change the structure. It's the whole point of resonance. It's just seeing how the electrons are dispersed within the structure. Sigma bond breaking changes the structure. When we move to mechanisms, we'll typically start with lone pairs and pi bonds first. Why? They're typically higher in energy. Okay? But we do have access to our sigma bonds. Move your electrons to an atom and look at the result. Okay? Stop focusing on, oh, the atom needs to change locations or the charge needs to change locations. Move electrons and say, okay, when I move those electrons, what was the result of that motion of electrons? That is much more difficult to go through and process. Okay? So our acids and bases. We got 2 structures here. Which is the acidic hydrogen in the 2 molecules? So identify the most acidic hydrogen in each of those molecules. And then between the 2 molecules, which one is more acidic? Okay. So I heard a couple things. I heard reference to the double bond. I also heard we're only looking at the hydrogens with the oxygens. Okay, why are we looking only at the hydrogens with the oxygens? Why are they polar bonds? Oxygen is more electronegative than hydrogen. It's also more electronegative than carbon. Why would I compare to carbon? That's where all the other hydrogens are located, to those carbons. That's what's going to help me differentiate between those charges. So I now have 2 hydrogens identified. Between those 2 hydrogens, which one's more acidic? The one on the left is more acidic. And what was your answer for it? Perfectly lovely answer. I remembered the functional group names. The functional group on the left is known as a carboxylic acid. The functional group on the right is known as an alcohol. Which of those could possibly be more acidic? Probably the one we call an acid. Why is it more acidic? This comes back to trying to minimize our charge. What happens if I remove the hydrogen? What would happen to that oxygen? It'd be negatively charged, right? We can remove that hydrogen. What happens to the other one? As a hint, it's the same thing. Becomes negatively charged. Negative oxygen versus negative oxygen. What's the difference in electronegativity? Nothing. What's the difference in size between an oxygen and an oxygen? Nothing. Why are they different acidities? Resonance. I can take the negative charge on the carboxylic acid and I can do resonance. I'm taking the electrons and I'm dispersing those electrons not on one atom but across two. What did I do? I've dispersed the electrons across a larger area. It's a size effect coming from the molecule. Okay? What we are doing is stabilizing that charge. We are minimizing it as best as possible. So when we go through and look at our acid-base rankings, you should be familiar with these 4 rules because I taught 152 and I know those are the 4 rules that I taught. Okay? Or ultimately just stated. Okay? I never really liked stating them. Okay? Rule 3 and Rule 4 are pretty much meaningless, but really what they are is an application of what we're going to now add as our Rule 3 and Rule 4. Stronger acids will have conjugate bases with more resonance. Okay, Rule 4, induction, hydrogens closer to electronegative elements will be more acidic. Those 4 rules you need to know like the back of your hand. Okay? And if you don't know the back of your hand, find something you know the back of. Okay? Maybe your mom's hand? Sorry. Know those rules. We'll pick up there on Thursday or Wednesday.